Good day, everyone. My name is Said Ahmad Ansari from American International University, Bangladesh. Today, I will present our work titled Performance Evaluation of Beam Steered Infrared Uplink in a Hybrid VLC IR System using Turbo Coding. The study evaluates how combining VLC downlink with IR uplink enhanced by beam steering and turbo coding can significantly improve indoor communication performance. RF systems in the 2.4 and 5 GHz bands are congested and often interfere with each other, making it difficult to meet today's high data rate requirement. VLC offers a high capacity downlink with existing LED luminaire, but it is sensitive to line of sight blockage and user motion. On the other hand, IR is eye safe, invisible, and more practical for uplink, but suffers from non line of sight attenuation and multipath dispersion. This motivates our hybrid VLC approach, VLC IR approach, where we use VLC for high SNR downlink and beam steered IR for mobility-friendly uplink, supported by turbo coding to overcome multipath and non-line of sight penalties. This image illustrates the full hybrid architecture. VLC LEDs on the ceiling provide the downlink and the user device detect these signals through photodiode receiver. For the uplink, the device uses IR transmitter with dynamic beam steering, directing the signal towards an IR receiver zone on the ceiling. The system is simulated in a 5 by 5 by 3 meter room and evaluated using metrics such as bit error rate, SNR, capacity, latency, and delay spread. Turbo coding is used to ensure robust performance, especially in moderate SNR uplink conditions. This slide shows the simulation environment. We modeled a 5 by 5 by 3 meter room with ceiling LEDs for VLC downlink and multiple IR transmitter and receiver for the uplink. The simulation grid uses 0.2 meter resolution and the model includes line of sight plus first order reflection. Beam steering is configured with plus minus 30-degree steering capability and reconfiguration time below 10 milliseconds. The system uses BPSK modulation and turbo coding rate 1 by third, enabling realistic evaluation of SNR delay and mobility effects. This slide contrasts VLC downlink with IR uplink behavior. The VLC downlink is strong because of direct line of sight from ceiling LEDs giving high received power, high SNR and very small RMS delay. By contrast, IR uplink is much more sensitive to pointing accuracy, reflection and user movement. Beam steering helps maintain alignment and stabilize received power across the room. The heat maps and plots clearly show the difference in the SNR distribution between VLC and IR channel. This figure shows the IR uplink receive power both as a 3D surface and the heat map. With the beam steering, the IR uplink achieves a smoother power distribution by pushing the energy towards the ceiling receiver zone even when the user is off-center. We can also compare this with the VLC downlink footprint, which appears much more centrally concentrated due to strong line of sight emission from the LED panel. This slide focuses on impulse response for line of sight and non-line of sight case. In line of sight, we see a strong early peak with extremely low delay, which yield high SNR and minimal ISI. In non-line of sight delay, multipath component appear, increasing RMS delay and degrading signal quality. Beam steering helps recenter energy towards the receiver, reducing this non-line of sight effects and stabilizing the channel. Turbo coding near Turbo coding provides near Shannon error correction performance, which is ideal for IR uplink where attenuation and multipath effects are significant. In our simulation, turbo coding achieves bit error rate less than 10 to the power minus 3 at about 8 to 10 dB, provide giving a coding gain of roughly 2 to 3 dB over the uncoded cases. The log map iterative decoding makes the turbo code highly resilient to temporal dispersion. We also compare alternative FEC schemes like LDPC, Polar, BCH, and RS code, noting why turbo coding was selected for a hybrid VLC IR system. Here we show how adaptive beam steering improves IR uplink robustness. The steering mechanism dynamically directs the IR beam towards the ceiling receiver zone at with a plus minus 30-degree range. The reconfiguration time is below 10 milliseconds, which is negligible compared to the coherence time of the indoor IR channel. Beam steering reduces multipath delay spread by approximately 30% and maintains reliable connectivity even when the user moves at a speed up to 1 meter per second. Before coding, the channel exhibits three important behaviors. The VLC downlink offers strong line of sight with high SNR at the room center with minimum delay spread. The IR uplink supported by beam steering is stable but is still affected by non-line of sight reflection. The delay characteristics show minimum delay and RMS spread at the room center, increasing towards boundaries. These variations emphasize the need for turbo coding to ensure reliable uplink performance at moderate SNR. This plot compares the turbo-coded IR uplink with uncoded IR, RF BPSK, VLC BPSK, and theoretical BPSK baseline. Turbo coding achieves bit error rate less than 10 to the power minus 3 at around 8 to 10 dB, providing a clear coding gain of 2 to 3 dB compared to uncoded IR. This curve closely follows theoretical BPSK performance at moderate SNR, validating the accuracy of our simulation. This makes turbo coding highly suitable for uplink communication in hybrid system. This slide presents the measured mean delay and RMS delay spread. Both metrics are small in a central line of sight region, but increases significantly near the room boundaries where multipath becomes stronger. Beam steering reduces delay spread in non-line of sight and shadowed area, improving timing performance and lowering ISI. This result further supports the robustness of beam steered IR uplink. We used k-mean clustering to group room position into low, medium, and high delay spread region. The silhouette score of 0.78 confirms that clustering is strong and meaningful. The frequency domain analysis illustrate how multipath introduces low frequency components that degrades the channel, especially in non-line of sight region. Beam steering improves the usable bandwidth by reducing this distortion. This slide shows the latency and throughput behavior after turbo coding. Throughput saturated at about 0.334 bit per channel use beyond 6 dB SNR. Latency decreases from around 580 millisecond at low SNR to around 380 millisecond at moderate SNR. This result shows that a hybrid VLC IR system can support interactive application and IoT traffic with modest delay spread. This slide compares our hybrid VLC IR system with conventional RF indoor network. Traditional RF system operate in crowded 2.4 and 5 GHz band where spectrum is limited and interference is high, requiring complex coordination to maintain quality of service. In contrast, hybrid VLC IR approach exploits the abundant optical spectrum with strong spatial confinement, which naturally improves physical layer security and reduces interference. The VLC downlink provides high capacity line of sight dominated transmission using existing lighting infrastructure. The beam steered IR uplink offers robust mobility and long line of sight performance even when the VLC path is blocked. Finally, turbo coding delivers bit rate below 10 to the power minus 3 at practical SNRs with moderate complexity, making this hybrid optical system a strong candidate to offload or even replace RF for indoor return links. To conclude, we propose and evaluate a hybrid VLC IR system where the uplink uses beam steered IR and turbo coding. Beam steering stabilizes the SNR and reduces delay spread, while turbo coding ensures bit rate below 10 to the power minus 3 at practical SNR level. This approach demonstrates that the IR can be a viable replacement for RF in indoor uplink scenarios. Future work include hardware prototyping, evaluating LDPC or polar codes, and exploring machine learning based predictive beam steering. Thank you for your attention. This concludes my presentation. Thank you.